Okay, so let us begin. So we had seen this theorem 3.2 of Alan Hatcher's book, which was about existence and uniqueness of Chern classes, that theorem. To my great surprise, I found that the analogous theorem in Fulton's book about Chern classes, its properties and existence, is also 3.2. So the goal of my lecture is to prove this theorem 3.2. What we will do today is, first I will go through whatever we did yesterday quickly, like maybe not recall everything, but the big picture I will recall. Stop me if you think that there is some if some explanation is needed. Either we can then and there sort it out or shift it to the discussion session. And so today I want to finish this main theorem, technical theorem about commutativity of intersection of two Cartier divisors. So that is one of the main goal. And then we will define Chern classes and prove splitting principle. That is the plan for today's lecture. It is possible that a part of today's lecture will spill over to the discussion, where some part of the discussion will be converted to a lecture. Okay, so that is because I have one more lecture and where I want to finish this Chern classes topic and prove this projective bundle formula. Okay, so let us recall the main players. So we have this Picard group. Okay, and from Picard group we managed to so there is this group of Cartier divisors modulo principal Cartier divisors. And there is this group of Cartier divisors without taking the quotient. Of course, this comes first. Okay, and this is the quotient map. What we observed is that Picard group is the same as Cartier divisors modulo principal Cartier divisors. Okay, and from Cartier divisors we could define a map to Zn minus 1 of x. Let's say dimension of x is n. So given a Cartier divisor, basically you can define order of that Cartier divisor at V using one of the locals f alphas, and doesn't matter which f alpha because they all differ by a unit wherever they are defined. And Zn minus 1 we have a map to An minus 1 x. Okay, this is quotient by rationally cycles which are rationally equivalent to 0. And the way this map is defined, principal Cartier divisors go to cycles which are rationally equivalent to 0. So this is something which is defined, and therefore since these are isomorphic, we have a way to go from line bundles to define cycles of codimension 1. Okay. There was explicit formula. So given a line bundle, how you actually define a Cartier divisor, I'll have to choose transition functions and make some choices. I cannot define a Cartier divisor uniquely up to a principal Cartier divisor. It will depend on what choices you make. But this is an isomorphism. So this is, in some sense, this is the first Chern class. Given a line bundle, I have a codimension 1 cycle. As I had mentioned, this can be written as A1x, A upper 1x. But this notation is typically used when x is non-singular, when this cohomology is defined so that so a direct sum of A upper kx is the analog of cohomology ring. But for homology, we don't have. So for singular varieties we don't have cohomology, so we are going to define Chern classes as operators. But this is the image that is sort of the Chern class, like before defining the operator. So where do
in all this x is a variety, right?
Huh?
X is a variety.
X is a variety always. Yeah, in some sense I think never I am going to consider x which is non-reduced or anything. So if at some point, then I'll mention that. So x is a variety. Yes. So where do pseudo divisors fit in? Okay, so pseudo divisors. Now, if you try to fit in this picture, you will understand the reason why they are defined. Pseudo divisors. So recall that they are triples L, Z, S. where L is a line bundle, Z is a closed subset, and S is a nowhere vanishing section of that line bundle defined outside Z. Okay, it is not a global section, it's defined outside Z. So if D is this pseudo divisor, remember support of D was Z, and to this pseudo divisor we associated a Cartier divisor, or we can just directly associate a cycle first, so which is given by order of vanishing of this section, right? Order of vanishing of this section. So locally this section is a rational function on any open set, and order of that function, rational function, has been defined. So basically I can define the cycle associated to this divisor in Zn-1 x. Okay. Now any line bundle is a pseudo divisor because I can take Z to be the whole of X, then I don't need to produce any non-zero section. S can be zero section. Of course, pseudo divisors, I can forget this Z and S and I get a line bundle. Cartier divisors give me a pseudo divisor because given a Cartier divisor D, the line bundle OXD has a nowhere vanishing section outside the support of that Cartier divisor. This was one of the things we defined. So I have a map like this, and a pseudo divisor gives a Cartier divisor gives a class here because it gives a line bundle, and then I can come back here. But if Z is non-empty, sorry, what am I saying? If Z is not equal to X, if Z is proper, okay, if Z is proper, then I actually get a Cartier divisor, well-defined Cartier divisor, because I take I take the Cartier divisor defined by this section. The problem with Z equal to X is the section may be 0, so I will not have a non-zero rational function. In that case, I only get so you can see that this pseudo divisor, this set of pseudo, this is not a group. Okay, I can add two pseudo divisors, but there is this Z, and so it is more like a disjoint union of Cartier divisors and Picard group, more or less like this. Basically, it gives us the flexibility of keeping track of the support when we can, and when we cannot, you just do line bundles, and so that is the idea. So any questions about this? Any part, any arrow which is not clear? Okay, then let us proceed. So now the point is, given a pseudo divisor, so let's say f from y to x is a morphism, and D is a Cartier divisor on X. Now, if this map is dominant, every rational function can be pulled back to a rational function, right? So I have the function field of X. So again, this is morphism of varieties. All my schemes will be varieties unless otherwise mentioned. So if I have a morphism of varieties, and if it's a dominant morphism of varieties, then I have a well-defined, then the function field of X injects into the function field of Y. Otherwise, I don't even have a map. Okay, so and in that case, so if F is dominant, or if F of Y is not contained in the support of D, so which means rational functions, I have at least some of the rational functions they pull back, then we can define, then F upper star D can be defined. We are not going to okay, so we will use this. So then F upper star D is defined as a Cartier divisor. Okay, so how do you define it? Cartier divisor is F alpha on U alpha. Take inverse images of U alpha, and basically F alpha. So I'll have to intersect. I take those U alphas which intersect this f of y, and ignore the others. And so since this is not yeah, so basically, yeah, what is the, so what I want to say is, if U is an open subset in X such that U intersects f of y, then any regular function on U which does not vanish on f of y can be pulled back to so any non-zero any function which is non-zero on f of y can be pulled back to y. I can restrict that regular function to y and it will be non-zero if it does not vanish on f of y. So similarly, if I have a rational function which does not have which can be written as numerator by denominator, both of which do not vanish at f of y, then I can pull back that rational function, which means that if this is not in the support, I can pull back. So the only case in which we are going to pull back Cartesian divisors are dominant maps. Okay, so but this is you can define it in this generality. But the advantage of pseudo divisors is I can always pull back pseudo divisors. So so if L comma Z comma S is a pseudo divisor, then f upper star of this D is defined to be f upper star of L. Then I take inverse image of this Z. Okay, it may be whole of y, it may not be whole of y. Then of course I pull back this section. This inverse image section is also nowhere vanishing. So the pullback of pseudo divisors makes sense. Okay, so this is the reason. Otherwise, we have to always do cases. Cartesian divisor can pull back, if not, make a line bundle. So this pseudo divisor language helps us avoid that. Sorry? Z is the support of that pseudo divisor. Yeah. So okay. So now we define this map. So if if D is a pseudo divisor, and alpha is, let's say, a cycle given by just one irreducible closed subvariety, then we can define D dot alpha. Let's say J is the map from V inside X to be equal to just the cycle defined by the pullback of the pseudo divisor. Okay, what does this mean? Cycle defined by the pullback of pseudo divisor. Pseudo divisor is line bundle comma Z comma S. I pull back the line bundle. If V is contained inside the support of the pseudo divisor, then forget it is just the line bundle. Okay. Otherwise, I also have a proper closed subset of V and a nowhere vanishing section of that line bundle outside that closed subset, and then I can define this at the level of cycles itself. If Z, the support of pseudo divisor, does not contain V. Otherwise, it is only defined as in A k minus 1 of X. So V, so this is in ZK of X, right? So that is the point. So one of the main things is that this is actually well-defined class in AK minus 1 of support of D intersection V. And this maps to AK minus 1 of X. Okay, this finer thing we are going to use. So this cycle is actually defined wherever you can come up with a actual divisor, Cartesian divisor, without ambiguity. So for example, if this is, so this is a statement. And then this D dot alpha. So then therefore we get, once I define it on the basis elements, we get D from ZK of X to AK minus 1 of X. This map, alpha goes to D dot alpha. And I had written down properties. So D dot, so this proposition, D dot alpha plus alpha dash equal to D dot alpha plus D dot alpha dash. This is actually sort of redundant because we defined it on basis and extended it as a group homomorphism. The second one is not redundant, but it's obvious. So D plus D prime dot alpha is D dot alpha plus D prime dot alpha. This is as an exercise. The third one is if OXD, this is the line bundle defined by this pseudo divisor, which means this line bundle. If OXD is trivial, then d dot alpha is 0. This is obvious because then this j upper star d is a trivial line bundle. What is the cycle defined by a trivial line bundle? Cycle may be non-trivial, but it is rationally equivalent to 0. Okay, so in ak minus 1 of x, it is 0. So this is 0 in ak minus 1. So anyway, d dot alpha is always defined in this ak minus 1 itself, not as a cycle. Only in certain cases we can define it as a cycle. The fourth one, I did not really complete the proof of this, so right now I'll do it. So f from y to x, or let's say x dash to x, is a proper map. Then f upper star of d, the pullback makes sense. The pullback of pseudo divisor is defined because basically I'm pulling back a line bundle. This dot alpha. Now alpha is in a cycle in x prime. Okay, so some k minus 1 cycle in x prime. So this, if I take the dot product upstairs, then push forward, this is equal to d dot push forward of alpha. This is actually going to be important for us. So let me go through the proof. So the proof is first without loss of generality, we assume alpha is equal to the class of V, and we can assume V is equal to x prime, and f of V is equal to x. So you'll see the great flexibility we have by working with non-singular varieties. Even if we wanted to work with, even if non-singular varieties were our great main interest, this kind of reduction will be so often made in the proofs. So I think I'll make it at least 2-3 times where we want to prove something, and we can assume that the cycle is actually the fundamental cycle of that variety itself. So we assume x equal to v. So therefore, like having theorems about non-singular varieties gives us great flexibility in the proofs. So yeah, so we can assume this, and now the non-trivial case is when v the function field extension, okay, is finite, and let us say it is n. Okay, so then what do we want to show? So we want to show that f upper star d dot product with v, okay, and then push forward is equal to n times the class of x, right? The degree times the class of x, because this x prime to, so v is x prime, so maybe I can write x prime here if you want. So this is my alpha, and or maybe this I want, let me write down the intermediate step also. This I want to show is f upper star d f upper star d, sorry, I think I made I jumped one step. So f upper star d, this I want to show is f upper star, this I want to show is d dot the fundamental class of the push forward of f lower star x prime. What is f lower star x prime? It is n times the class of x, right? So this is n times the class of x, n times the class of x. But what is d dot x? The class, the divisor defined by d, right? If it is so we want to prove this. So there is a small nuance here, like in the proof which I had missed yesterday, so I paused and I postponed this proof, and the point is the following. So we want to prove this equality where? In ak minus 1 of x, okay? But now here is the trick, so which is that choose a let choose a Cartier divisor which represents d. Okay, so d is a pseudo divisor. If the pseudo divisor support, like if this z is whole of x, then I cannot, then a Cartier divisor is only well defined up to principal Cartier divisors. so I'll have to make a choice. If z is not whole of x, then it's actually uniquely defined. So let d tilde, or I'm going to call it d only. So let d represent, choose a Cartier divisor representing d. Let's call it d only. So for a Cartier divisor I have to do this, and that is not a problem because pullback of Cartier divisor is defined because in this case you see this is a dominant map now, v to v prime, because I replace x with f of v. So I have a dominant map, so f upper star d is defined as a Cartier divisor. So I'm going to prove this for Cartier divisors d. That is good enough, right? Now why this reduction? This reduction allows me to prove this equality at the level of cycles. Because if I take a Cartier divisor and I'm taking dot of something which is not contained in the support, then that dot product makes sense as a cycle, right? So we have to prove this equality as a cycle. So therefore we have to prove this equality as cycles. And because we have to prove some equality of cycles, I can do it locally. That is the reduction. So therefore we can prove this locally on x because it's an equality of cycles, okay? And now so locally every Cartier divisor is a principal Cartier divisor, like f alpha u alpha. I replace x with u alpha, okay? So locally it is a Cartier divisor. So let's say, so therefore without loss of generality we assume that d is, let's say, the Cartier divisor given by one rational function. That is our notation for Cartier divisor given by one rational function, let's say r, okay? And then now let us plug this and see what happens. So what is f upper star r? It is just r considered as a rational function above, the pullback of the rational function. So f upper star above, and then dot product with x. So this is just the Cartier, this Cartier divisor itself, right? D dot x is just the class defined by that Cartier divisor. So therefore so if I pull back this and take the dot product, this is just the class defined by the Cartier divisor defined by f upper star r, and then I push this forward. This we have proved in this proper push forward, this result on proper.
You can call that near the way divisor of a upper star.
Yeah, maybe I should call it way divisor of upper. Yeah. So what is the notation for way divisor?
Square bracket of
square bracket of f upper star r. Yes, this is so this is the square bracket of and then when I apply push forward, it is equal to this, right? So I'll just pause for 30 seconds in case you want an opportunity to ask something. Yeah.
How did you reduce it to cycles?
How did you reduce? Yeah, so the reduction to cycles is, see, I want to prove this for every pseudo divisor, right? How do I actually define d dot something? So what I can do is, for this pseudo divisor, choose a Cartier divisor, right? When the Cartier divisor is defined, okay, and when the dot product makes sense, in the sense when the, let's say in this case, this dot product is well defined as a cycle first. So let me go back here, okay, so where this v, so suppose v is such that this support of d does not contain v, right? Suppose it's a Cartier divisor, support does not contain v, then the pullback of, let's say for example v is whole of x, right? That is the only case we want. Then in that case, this d dot alpha is actually well defined as a cycle, right? First, and then of course we are, because we don't know for which alpha this is well defined as a cycle, we always take this as the target group. But for this particular case, I am first going to prove this equality as cycles first, because I'm looking at the recipe as how this is defined as in AK minus 1. the way it is defined is at some stage you actually get a cycle and then take its rational equivalence class, because I have the choice of Cartier divisor may not be well defined. Okay, so but what I'm saying is choose a Cartier divisor. Okay, it may not be well defined, but because we have chosen, but choose it, and then I have to prove this for.
Just for clarity, at that equation, second last line, at the end you write belongs to z n minus 1.
Yeah. This is correct. N minus 1 of x. Okay, so yeah, right. So in fact, that this allows us the flexibility to do it locally, and now locally you see, then it is just the theorem that was proved in Nitin's lecture, that if I take f upper star, if I take the weight divisor of this function and push forward that, then I get the weight divisor of the norm of that function, right? So this is equal to the weight divisor of the norm of R. But R was already coming from the base field, so its norm is just equal to n to the power the weight divisor of R. Yeah, norm of f star R. Yes, yes, correct. Norm of f star R. So this norm of f star R, and then that is equal to R to the power n. Its weight divisor is n times the weight divisor of R. And then that is exactly equal to the right hand side, because this is R and R dot X is the weight divisor of R, and then n times R. So this proves the projection formula. This projection formula is going to be of great help because as you will see that in this theorem. So what is the main theorem that we want to prove now? So again, I made a mess in stating this theorem yesterday. I said pseudo divisor instead of Cartier divisor. So this is then I think somebody pointed out, you pointed out that some well-defined problem. So we are going to, so this is the statement. So if D and D prime are Cartier divisors on X, then what I can do is I can take the cycle defined by D prime and then take the dot product of this. Remember, dot product is only defined as a class, modulo rational equivalence. Okay, I want to show that this is equal to, now D prime can play the role of Cartier divisor and D can play the role of a cycle. So this equality holds. This is the main theorem of
right into a n minus 2.
Correct. In a n minus 2x. Yeah, that is a good suggestion, because this value group is actually it's important to keep track of that. So this equality we have to prove. Okay, before we proceed, let us see what are the advantages of actually proving such a thing. So yesterday I had mentioned, so this is sort of repetition, but if you don't remember, then here it is again. So corollaries. So what is the benefit of proving this commutativity? So of course, later on when intersection products are defined, perhaps this is also used to show that the intersection of cycles is commutative. But even right now, here is the corollary. Okay, so for any pseudo divisor D, okay, D alpha goes to D dot alpha. So D dot so we had a map from Z k of x to ak minus 1 of x. So D, where alpha goes to D dot alpha. This induces a map from ak of x to ak minus 1 of x. So this induces a map from, or this factors through is a better word. So for this factors through ak of x. So which means, what it means is, if alpha is rationally equivalent to 0, then D dot alpha is actually 0 in ak minus 1x. Okay, so this is what we will get. And then for a given Cartier divisor, for a given pseudo divisor, or let's say given line bundle, now line bundle is also a pseudo divisor, this operation akx to ak minus 1x will be the first Chern class. So for all k I have this operation, and we said that for singular varieties our Chern classes will be these operators. Okay, and when we define intersection product and this Chow ring for non-singular varieties, they will actually be elements of of that Chow ring. That will be straightforward, like how we have constructed. So right now let's just focus on them. I'll come back to this first Chern class again. So this fact, why is this true? So why is this true? Because so proof of this corollary. Okay, so proof of this corollary. So without loss of generality, you see, what are all the rationally equivalent cycles in Zk of x? They are the group rat k of x is generated by something. What is it generated by? I have a subvariety w, and I have the weight divisor of a rational function on w, right? These are the generators. So I can replace x by w, right? So without loss of generality, I can assume that alpha is actually the weight divisor of a function, of a non-zero function on x. So if you are very careful, you will see that the fact that this factors through the support of alpha, that is actually sort of used here, but I'm going to sort of not over discuss it. So alpha is equal to, we can assume that alpha is actually weight divisor of a function. Okay, because and x, right? Because I can replace, so I look at the generators of rat k of x and look at one generator. I'm going to send it to 0, so that is w. Replace x by w, and now I'm going to show that that d dot alpha is 0. Okay, but what is d dot alpha? So d dot alpha. Now alpha is also defined by a Cartier divisor. This is equal to the Cartier divisor defined by alpha dot the weight divisor defined by d, because of this theorem. Now my alpha, if alpha is a Cartier divisor, which by my reduction, so this is the reduction, this 4 letters, so then I can interchange that order, and this dot, it is equal to this dot this. But whenever the pseudo divisor or the line bundle that I am taking dot product by, if that line bundle is trivial, then this dot product is 0 in a n minus 1 of x, or there was some reduction, like we started with k, so then x was k dimensional, and therefore this is in ak minus 1 of x. Okay, so right, so this gives a.
You made a comment about the support of d.
I made a comment about support of d. See, I want to show some class is 0, right? Now I can of course assume my cycle is cycle of w, right? So now, so I have this zk of w map here, and this maps here, and I have d dot on this zk of w to ak minus 1 of w. Okay, what I'm saying is this map is anyway defined such that it factors here, so therefore I can consider the top arrow. So I would like you to think of this reduction without loss of generality. So in fact, the reason I wanted to think is this technique is so common that it is good that if you actually go through.
May I nitpick your notation a bit?
Yes.
In that last line there, the Cartier divisor should write as div r.
Div r, yeah. So I was struggling to find a good notation. Div r is a good notation for Cartier divisor. Now you can copy paste for. Okay, I'm going to erase that anyway. So henceforth, Cartier divisor of a rational function will be div of r. Okay, so right, is this clear? So this is going to be useful, and we are going to struggle to prove this. Struggle in the sense it's going to be a little bit of lengthy proof, but not very difficult. Like individual steps are easy to understand. Okay, so it's just that if we put them all together, it's lengthier than what we have done right now. So proof. Let us start with the proof. So the first thing is reduction to the case when, see, finally we want to reduce this case to commutative algebra. Okay, so like of course I can assume X is affine and all, but by commutative algebra I mean if it will be good to have D and D prime defined by actually elements of my ring, so then I can actually take quotients and things like that. So we would like to so step 1, this is reduction to the case where D and D prime are effective. Okay, let's first reduce it to this case. Okay, so where D and D prime are effective, sorry, not effective. Yeah, effective Cartesian divisors. So I want to reduce it to this case. How do I reduce it to this case? So the trick is follows. So first, let us show that we can reduce to the case where D is effective, one of them is effective, and then similar argument will show that we can reduction will be used to show that D prime is also effective. Okay, so first assume the statement holds for all when D is effective. Okay. So what I'm saying is whenever D is effective in this, I will handle D prime later, but first assume that D is effective and assume that this holds for every D prime and D effective. This holds for every D effective and every D prime on every X. Okay, X also will change. Okay, so if this theorem holds when one of the Cartesian divisor is effective, then the theorem holds for all D and D prime. So this we will, so then we claim, then we will show that it holds for all D. Okay, so if I show that if D is effective, then the statement, if for effective D it is true, then it is true for all D, which means I can focus my attention to proving it in the case when D is effective. Okay, so similar reduction we will also make for D prime. How do we do this? We already discussed this yesterday. So I mean, I'm not saying that discuss the proof. The main idea is as follows. So let I be the ideal sheaf of denominators of D. So what was this? Recall that this was defined by IU is set of all x in OX of U such that x times OXD of U lands up in OX of U. Okay. So since yesterday's tutorial we spent on this, I am assuming that I need not spend more time on this. So this is what I need is, so if this notation is confusing you, what I am doing is I have just cooked up an ideal sheaf such that I times of OXD is contained in OX. Okay, here OXD I am implicitly assuming it to be a subsheaf of the constant sheaf of given by function field. Therefore, this equality containment can be talked about. So I just want some ideal sheaf. It's not important for me that this is exactly this. Something smaller is also okay. So I have this ideal sheaf. Now blow up this ideal sheaf. So x tilde is the blow up of this I, blow up of x at this ideal sheaf I. Okay. And let's say pi is the morphism from x tilde to x. Again, one of the results I want to assume from yesterday's tutorial is that if I pull back D, if I pull back the Cartesian divisor to x tilde, so pi upper star of D actually is E minus some effective divisor where C is effective. C is effective. Okay, so we did this yesterday. So because pi inverse of I times the OX of the pullback of D is an ideal sheaf, both these are locally principal. First take the Cartesian divisor. So the Cartesian divisor associated to I is E. Actually the Cartier divisor associated to I is minus of E. Okay, so that is the Cartier divisor associated to this is D, and whatever the Cartier divisor associated to this is, that is minus effective divisor. So therefore we get this E minus C. So on X tilde, my D becomes difference of two effective divisors. It's not very important what those exactly divisors are. It's difference of two effective divisors. Now I'm assuming that the theorem holds when one of the divisors is effective. So therefore by assumption, okay, so I know that so if I try to calculate pi upper star D dot this pi upper star D prime, okay, what is this? So this is equal to E minus C dot pi upper star of D prime, but any addition here gets distributed, so this is equal to E dot pi upper star D prime minus C dot pi upper star D prime. Okay, but E and C are effective. So for effective, I know that I can interchange the order. It commutes, right? That is the assumption. We are going to prove the effective case later on, but we are assuming that if one of them is effective, then the result holds. So therefore, this is equal to pi upper star D prime dot E, and this is equal to minus pi upper star D prime dot C. But again, pi upper star D prime, the addition, whatever cycles I am taking, I can actually just club them together. So this is equal to pi upper star D prime dot pi upper star of D. Right? Is this clear? This equal to this. It is just using the fact that this dot operation distributes over addition in both variables, and I know that it commutes when one of them is effective. So this is just following that. Okay, so I get this equal to this. Now I am going to push forward and use projection formula. Okay, so pi upper star of what is, so therefore pi upper star D dot pi upper star of D prime. What is this? Let us first calculate this. This by projection formula is D dot pi upper star of pi lower star of pi upper star D, right? D prime, yes. This is equal to this, right? I claim that this is equal to D prime itself. If I take D prime, I pull back and push forward, I get D prime itself, because this is a birational morphism. Okay, so so let us observe this. So the claim is that see, D prime is equal to D prime is equal to D prime dot of X, but X is push forward of, this is equal to D prime dot pi lower star of X prime, right? So now I use the projection formula in the reverse way. And so why is this X equal to pi lower star X prime? Because this is a birational morphism, and therefore the fundamental class, the degree of extension is anyway 1. So on an open set, so therefore I have this, and now this is equal to pi lower star of pi upper star D prime dot X prime. But this is the class given by pi lower star D, pi upper star D prime, right? So therefore this is equal to pi lower star pi upper star D prime, the class. So, or maybe I am putting the, maybe here, this also maybe should be like this. Okay. So therefore this is nothing but this push forward is nothing but D dot D prime. This whole thing is D prime, and and the other push forward is D prime dot D by the similar reason. Okay, so therefore we have proved the theorem. Have we proved the theorem? No. We just said that if the theorem is true when one of them is effective, then it's always true. Similarly, now if the theorem is true for when the other is also effective, it is true, it is proved using the same thing. Now I have to only prove the theorem when D is effective. So now I can also assume D prime is effective, because I can do the same thing, take the ideal sheaf of denominators of D prime, blow it up, D prime will become difference of effective divisors there. Now D remains to be effective, and then similar came. So this I am going to leave it to you. So similarly, we reduce to the case when D prime is also effective. Okay. So that is, we want to now prove the theorem when both D and D prime are effective, and the reduction to D and D prime effective was using projection formula and the fact that if you blow up the correct ideal sheaf, any Cartier divisor becomes a difference of effective divisors. So therefore now henceforth we will assume D and D prime are effective. Okay, D and D prime are effective. Now this effective case also I am going to split in two parts. So first we will prove that the case when D and D prime intersect properly. Okay. So case 1, D and D prime intersect properly. Okay. So first of all, remember, effective means the divisor associated to that that Cartier divisor, that is actually a given by the fundamental class of some subscheme, right? And what does intersect properly mean? So if I look at support of D intersection support of D prime, then there is no component of codimension n minus 1. Okay, all components have n minus 2. They cannot have codimension greater than n minus 2 because of Krull's principal ideal theorem, right? Both are sort of locally principal, this D and D prime. So let's say, now let us switch to commutative algebra. Let's say x is equal to spec A, and D prime are they are Cartier divisors. Let's say they are principal Cartier divisors given by just one function, but now that's because they are effective, so they are given by elements of A. So let's say D and D prime are defined by A and A prime in this ring. Okay. Let us assume that. That we are not assuming that, we reduced it to this case. So D and D prime are given by this A and A prime, elements of A and A prime. And what we are saying is, look at the ideal generated by A and A prime. So, or let's say D intersection D prime. So look at the ideal generated by A and A prime. What can you say about this? This has, so every prime ideal containing this has height at least 2, right? This is, so basically the other geometrically no component of the intersection is a divisor, because I am intersecting divisors. I do not want to end up getting another divisor in that intersection. That is not proper intersection. Okay. So now let W be a dimension n minus 2 subvariety of A. So subvariety of X. And what I'm going to do is, I'm going to analyze what is the coefficient of D dot D prime at this W and D prime dot D at this W, or maybe not at one W, but maybe yeah. So at I want to analyze the coefficient of W in both these things that I want to show equal, D dot D prime and D prime dot D. Okay, so in fact what I'm going to do is, I'm going to replace, so I don't want to assume X equal to spec A. Let's just assume that X is some affine scheme such that D and D prime are given by equations A and A prime. And now for a subvariety W, let A be equal to the local ring of W at X. Because I want to look at what are coefficients of this intersections at W. If I show that the coefficients are the same for any dimension n minus 2 subvarieties, then they will be equal, right? Because after all, it is summation of all n minus 2 dimensional varieties with coefficients. I have to show coefficients are equal. I'll show this for one n minus 2 dimensional subvariety at a time. So let A be this local ring. So and now A is this local ring. So what is and let's say V is a height 1 prime ideal. So V is let's say yeah. So V.
Sorry to interrupt. Always prove here in detail in my.
Yeah. Actually, what I can do is maybe skip this part.
Yeah,
Shall I skip this?
I've only done this intersect properly if it's still
Okay. So then yeah. So that is a good idea, so that I can finish things. So maybe if there are some discussion sessions with sufficient time, this can be done. Maybe not today's discussion session. So, but this let us assume effective Cartier divisor. But I will just say what is involved. What is involved is you have to explicitly write down the cycles, because you see order. Given a Cartier divisor, I can write down the cycles using order, which is the length of certain Artinian local rings. You write down, and then using commutative algebra, you have to actually show equality. Okay, so it's a pure commutative algebra proof. There are I found some tricky parts, but I'm sure so this like reading this notes will be so let me just assume this. Okay, so let's assume this. So refer to notes. Okay, so. And yeah, so it's a very interesting commutative algebra argument. So I would like you to actually go and read it if possible by today. So general case, let us look at general case. So we have so now what do we have? We only need to prove the theorem for effective divisors, and we know the theorem for effective Cartier divisors which intersect properly. Okay, modulo the proof in this notes. Now we want to handle this general case where the intersection of two Cartier divisors might contain a higher dimensional, like actually another divisor. So that is the case that we want to handle. So now let D and D prime be any be effective Cartier divisors. Okay, let D and D prime be effective Cartier divisors. Now I want some integer which will tell me how far they are from intersecting properly. Okay, so let me define this epsilon D comma D prime. This is the maximum of order of D at V multiplied by order of D prime at V, where V in X is a dimension n minus 1 subvariety. Okay, let us understand what this is. So when will they not intersect properly? If there is a dimension n minus 1 subvariety which appears in the divisor of D and which also appears in the divisor of D prime, right? Then they will not intersect properly. But how is a divisor defined for a Cartier divisor? I take the order of D at the local ring of that n minus 1 dimensional variety, right? So order of D. So if there is a V such that both this and this are non-zero, then they are not intersecting properly, right? And so if for example any n-1 dimensional variety, either order of D at that V or order of D prime at V is 0, it means that there is nothing common of n-1 dimensional in the intersection, and that means they are intersecting properly, right? So therefore epsilon D prime equal to 0 if and only if D and D prime intersect properly. Right, if and only if. So this is an integer which, so for example, what we are going to do is we are going to blow up D intersection D prime. Okay, this subscheme D intersection D prime, and then we'll observe that things get better above. So even if they are not intersecting properly below, this integer, this is I think called excess or something, some name is given in Fulton's book, but this integer which is measuring this bad behavior or bad behavior in the sense of not intersecting properly, this integer gets drops. Okay, that is what we are going to prove. Once we show that, again we can, if something becomes better over after a blow up, and the formula holds there, we can use projection formula and come back below, right? That was a similar trick as we did when we reduced to the case of effective divisors. So that is the idea. So what we want to show is the following. Okay, so now let x tilde be the blow up of x at D intersection D prime. Let this be the blow up of x at D intersection D prime. Okay, and so now here is a claim about this blow up, and we will have to. So here I am going to assume that these are effective Cartier divisors. Let's say. Okay, maybe let me write the reductions in the correct order. Let's so we can assume without loss of generality that x is spec A. Okay, so these reductions also need some thought, you see, because again I am reducing to an open set, so it's important that I am showing equality. So this same trick I mentioned in the projection formula. So somewhere you have to switch from cycle classes to cycles, only then I can shrink open sets. But I have explained it once, I don't want to go through it again. So x equal to spec A, we can assume x equal to spec A, and D and D prime are so D is divisor of A and D prime is divisor of A prime, where A and A prime are actually in my ring. That is what effective means. Okay, so right, so that is what effective means. So this is the situation, and now what I'm going to do is I'm going to take this ideal I which is generated by A and A prime. This is nothing but this corresponds to D intersection D prime. So this is the ideal of the intersection of D and D prime. Okay, I'm going to blow up this ideal. So let x tilde be the blow up of x at this ideal I. Okay, now there are some things which are going to happen on this blow up. So let me list. So the first claim is that pi, so again pi is the map from this blow up to x. Pi upper star of D, if I look at pi upper star of D, this can be written as the exceptional divisor plus something. This is obvious, it can always be written as exceptional divisor plus something, because you see, what is the exceptional divisor? It's the inverse, it's given by the inverse image of the ideal sheaf that I'm blowing up. That is the exceptional divisor, right? And D contains the zero locus of that ideal sheaf. So if I take inverse image of D, it is going to contain the exceptional divisor. But of course I'm claiming that it contains with coefficient 1. So this, we need local calculation to actually check this. So and pi star D prime is equal to E plus C dash, okay, where C and C dash don't intersect. Okay, so C intersection C dash is empty.
First of all, what are C and C dash?
There are some effective divisors.
That you are not saying.
Correct. So where C, so there exists, okay, so the claim is, yeah, let me say that. There exists effective Cartier divisors C and C dash, okay, Cartier divisors, such that pi upper star D is E plus C, pi upper star D dash is E plus C prime, and now there is something better about C and C dash, namely that they don't intersect, so I don't have to worry about whether they are intersecting properly or not, and their intersection with E is such that E of, so, and if E of D dash is greater than 0, which means I am in the case where these divisors are not intersecting properly, in that case the excess or this epsilon of CE is strictly less than epsilon D dash, okay, and epsilon of C dash E is strictly less than epsilon of D dash. This we have to actually, without fear, we have to write down the local coordinates of the blow up and unravel the definition, what is divisor of a function, length of some ring, everything, and maybe use and also use projection formula, and then we have to do this. It's not a very difficult argument, so but let us first see that if this happens, then we are done, okay. So this this excess gets reduced, okay. So this is what we have to show. Now what I want to say, so this we will do in the tutorial, so the discussion session, okay. So because I really want to do splitting principle and churn, define churn classes in the remaining time, okay. So I would like to actually work out this prove this using local coordinates on the blow up, so it will give you some more practice of working on the blow up of ideal sheaves. So so this claim is postponed to discussion session, okay. So but modulo that claim, let us see that we are done with this this theorem. Why are we done? Because by induction on this invariant epsilon D prime, assume that the theorem holds for no, we already know the theorem holds for epsilon D dash equal to 0. Assume it holds for certain integer, and then you see the theorem holds for C, the pair CE, which means C dot E is equal to E dot C. It holds for C dash E, C dash dot E is equal to E dot C dash. It holds for C dash because they don't intersect. So not intersecting is supposed to be proper intersection. So then so every pair of divisors that appears in EC and EC dash, for them the theorem is known by induction, right? So therefore by induction on epsilon D dash, okay, so where D dash are now or let me just say by induction on epsilon, okay, because epsilon of the device is involved, we know we have that if I look at E plus C dot E dash, the divisor defined by E plus C dash, my claim is that this is equal to E plus C dash dot E plus C. These two are equal. Why? Because yeah, you have to use distributivity, so you have to distribute and separate, write 4 terms, and each of the terms will have epsilon which is less than epsilon of D dash, okay. So what we are actually going to do is again blow up and still the epsilon becomes 0, which means they properly intersect. So therefore by induction I have this, and which means pi upper star D dot pi upper star D dash is equal to pi upper star D dash dot pi upper star of D. And now we have already checked that if I push forward this to x, I get D dot D dash, right? So therefore by projection formula d dot d dash is equal to d dash dot d. Okay, so this needs some argument, but it was done in before when we reduced to the case where the divisors were effective. That push forward of this is actually d dot d dash. Okay, so there you have to use projection formula twice. Okay, so we are done with the proof. There are two missing steps. One is that commutative algebra step, which is left to you to refer to the notes, and the other is this calculation on the blob, which we will discuss in the discussion session. So this finishes the proof of commutative modulo that. Now let me go to churn classes. Actually, before that, I will define this Giessen map for divisors. It's just a comment actually. The hard work is already done. So for divisors, so or let's say effective Cartier divisor. Let's say D inside D is an effective Cartier divisor. So now there is what it means is D is actually given by a subscheme of X, right? So D, I will think of D as a subscheme of X. So it could be, in this case, it may not be a variety. It could be a scheme with multiplicities at the components. So let's say I from D to X is the inclusion. So it's a divisor which it's a one codimensional subscheme which is locally given by one equation. Such a thing defines a Cartier divisor, and that will also be denoted by D by abuse if you like. So now the point is, if I have a cycle in AK of X, we have already seen that D dot alpha is well defined as a cycle in AK minus 1 of X, but not just that, it is well defined as a cycle in support of D intersection support of alpha, right? I want to ignore this. I will increase the set, so it's well defined in AK minus 1 of support of D. But now I am already thinking of D as a subscheme, so I'll just say that it is well defined as a
ZKX. Alpha is from ZKX.
Yeah, it is in ZKX, but because of this commutativity, we said that the map actually is induced on AKX to AK minus 1x, because rationally, so the map induced on AKX also I denote by D dot alpha, alpha goes to D dot alpha only, right? So so if I take a class here, then D dot alpha is actually defined here, not just in AK minus 1 of x, okay? In fact, for individual alpha, I can also shrink this to D intersection support of alpha. So therefore we have a pullback map. I upper star, we will denote it by I upper star, from AK of X to AK minus 1 of D. So this is a pullback map from AK of X to AK minus 1 of D, where alpha goes to D dot alpha. All the verifications are the same. So like if alpha is rationally equivalent to 0, then D dot alpha is rationally equivalent to 0. So all that has already been done. So therefore this map is well defined, and this is called the Giessen map of divisor. So it is the pullback along a effective Cartier divisor.
Just make one more comment.
Yes.
This is not flat, but the relative dimension is minus 1.
Yeah. So this is not flat. You can think of the relative dimension as minus 1 if I just subtract dimension of D minus, and therefore you see this normally if you pull back, AK goes to AK plus relative dimension, and therefore this minus 1. You can fit this in that picture. So we have this map, and there are some obvious things that the obvious properties of this which need not even be proved because they follow from what we have done. So let me just state them. Yeah, let me just list some properties because later on they may be needed. So first is that if OXD is trivial, then this implies that I upper star is 0, is a 0 map. That can be observed at the cycle level, because if D is trivial, D dot alpha, the way it is defined, it will be 0, right? So it will be rationally equivalent to 0. Not rational, this is anyway defined as a class, so that will be 0, right? So this is this again follows, because if D is trivial, then D dot alpha is trivial. In fact, yeah, so I hope this is clear. So stop me or ask me if something is not clear. So I'm just claiming that these properties are something we that follow from what we have done already. I'm not going to prove them, so therefore stop me if they are not clear. So second is that what happens if I take I upper star alpha and then I push it forward. I upper star alpha, I push forward alpha. You see, if I apply I upper star alpha is D dot alpha. When I take its image in AK minus 1 of X, what I am also denoting that by D dot alpha only, now considered as a cycle on X, right? The notation was D dot alpha. So the claim is that this is equal to the first Chern class of OXD dot alpha. Why is it the first Chern class dot alpha? Because first Chern class was defined as this operator as alpha goes to D dot alpha. That was the definition of the first Chern class. Maybe I should write it down. So
first write it equal to D dot alpha.
yes, okay. So this is D dot alpha considered as a class in AK minus 1 of X, and this was the definition, or if you like, I am defining it right now, C of OXD dot alpha, right? Or in the book, sometimes this cap alpha notation is used. Cap means instead of because cohomology acts on homology, that action is denoted by cap product. That's why this notation. So if you prefer dot, you can put a dot there.
And dot is reserved for cup.
Dot is reserved for cup. Okay, that is that may be correct. So that is one reason why you want to replace dot with a cap, but that is a minor thing. So let me just leave it to you. So the second thing is, what happens if I take a class in D, push it forward and pull back? Okay, this is an exercise. The claim is this is equal to C1 of n cap alpha, where n is I upper star OXD. So this I am going to leave as an exercise. So it is just a revision of the definitions. Because let me just leave it as an exercise. So fourth, there is no fourth property. This is all. Okay, so now let us see. Let us go to Chern classes. Theorem 3.2. That is our goal. So now I'm going to write down the definition. So if L is a line bundle, okay, then we have C1 of L. This is an operation on AK of X. We have for all K. Okay, so AK of X to AK minus 1 of X, which is alpha goes to C1L cap alpha. And what is this? This line bundle is also a pseudo divisor. So this is our D dot alpha. So line where the D is now L considered as a pseudo divisor. Okay, so this operations are called the first Chern class. Okay, so our higher Chern classes are also going to be operations, and as I said, for non-singular varieties they will actually be classes in the cohomology ring, the analog of cohomology ring, which is the Chow groups indexed by codimension. So now I want to define higher Chern classes. Okay, so they will also be operators. So we want to define Ci of L. These will be operators from AK of X to ak minus I of x. Okay, let me just make a note here. So when x is non-singular, okay, later on it will be clear that when the things are set up, it will be clear that Ci of L will actually be a class in Ai of x, A upper I, this is indexed by codimension, and this operation is nothing but take a codimension I cycle, intersect it with codimension k cycle, and then you get this correct dimensional k minus I dimensional cycle. So they will actually be classes. So if this operator sounds like not the correct thing, so for non-singular varieties it will be more of what you expect. So what are these Chern classes? So we want to show existence, uniqueness provided the same theorem 3.2 we want to show. So first what we will do is we will define what are called as Segre classes. So okay, so let E be a vector bundle of rank E plus 1. Okay, so let E be a vector bundle of rank E plus 1, and then I take the projectivization of E. Let's say this map to X is pi, and on this projectivization I have this line bundle O1. Okay, let's say this projectivization I just call it P if needed. So O1 is this line bundle on this projectivized bundle, and now so define, so for an integer I, define Si of and let's say an alpha in ak of x. Okay, so define Si of alpha to be the class which is pi upper star alpha, pull it back to this projectivized bundle, then take cap product with C1 of this O1. So I need bigger space. So take this first Chern class of this O1.
O1 is the dual of the topological.
O1 is the dual of the tautological bundle, correct. So take the first Chern class of O1, okay, and then raise it to the power E plus I. What does raising to the power E plus I mean? Intersecting, yes, for non-singular varieties, but right now I have to just compose the operators, right? So when I view Chern class as operators, multiplying the Chern classes just means composing those operators, right? So, and in the case of non-singular varieties, it will be intersection. So raise it to the power E plus I, okay, and then cap product with pi upper star alpha, okay, and then push all this forward to x. Okay, so this and pi lower star of this. Right now, don't worry about the exact formula. You'll soon start. It's not actually very complicated. I'm just taking the first Chern class of O1, raising it to the power E plus I, and then capping it with the pullback and pushing it forward. Okay, I don't have O1 below. Otherwise, I would have done it below only. So this is not, it looks lengthy on the board, it's not a very complicated formula, but the formula is not important. What is important is whether the Chern classes we define using this, whatever this SI Segre classes are, whether they satisfy the properties that we want. So, okay, so what is this SI? So SI is a map from operator or map from AK of X to AK minus I of X. Now you have to check, is it really from AK of X to AK minus 1 of AK minus I of X? Because if I pull back, AK of X is pulled back to what? I'm pulling back by a flat morphism of E plus 1, right? And then, sorry, not E plus 1, E. I'm pulling back. This is a flat morphism of relative dimension E. So this is in AK plus E of this top space. And then I'm applying the first Chern class operator E plus I times. So it will land in ak plus I minus e plus I. So I will cancel, so it will be, E will cancel, and then I'm left with this. So therefore this ith Segre class is a map from ak x to ak minus I of x. Okay. So it is, a priori it is not even clear whether SI is 0 for I negative. Like, immediately it's not clear, because maybe if I is negative, this is still positive, and maybe I get a non-zero push forward, maybe. So we will show it is 0, but right now it is not clear. Okay, so now let S of E. So because the negative SI are going to be 0, we'll prove that next time. I'm going to define the total Segre class to be 1 plus S naught. Sorry, the S naught is also going to be 1. So I'm going to define it to be 1 plus S1 of E. I'm just going to take Segre classes from 1 onwards, and times T is just some formal parameter, so a variable T square plus dot dot dot. Okay, this is a power series starting from 1. I'm going to take the formal inverse of this. So define C of E, which I'm going to write as 1 plus C1 of E times T plus C2 of E times T square plus dot dot dot. This is the formal inverse of the Segre class. So what does formal inverse means? Give me a minute. So formal inverse of S of E. Okay, and now. So what I mean is, if you look at the polynomial 1 plus a1t plus a2t square and so on, it is invertible as a power series. Let's say in Z power series t, it is invertible. So formally I can invert and see the coefficients. So I'll get some expressions for Ci in terms of Si. We can write it down very explicitly. So C1 of E will be equal to minus S1 of E. If you don't like this formal inverse stuff, then this is the formula for defining that the Chern classes. So this is minus of C1 of, and by induction Cn of E is minus of S1E times Cn minus 1, or maybe let me just S1 Cn minus 1 plus dot 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 up to Sn. Okay, so S1 Cn minus 1, S2 Cn minus 2 up to Sn. Okay, so C0, I don't want to write C0, that's why I just Sn. Right, this is the explicit formula. If this is not making sense, then just take this as formula, direct formulas for Chern classes. So we have defined Chern, and then you can see that Ci are actually, so using this explicit formula, you can actually, this is an exercise that they are exactly, this again exercise is trivial, you can do mentally, that Ci are actually, because Si are operators of degree minus I, Ci are also operators of degree minus I. So Ci of E, these are operators from Ak of x to Ak minus 1 of x. Yes?
How are we defining Si of E?
Sorry, this is Si of E. Sorry, my Si. So I have dropped this E because this E was fixed. But this operator Si, which depended on E, is called Si of E, right? It depends on E. So these operators are Chern classes. Again, if X is non-singular, they are actually going to be classes in A upper I of X, and that is clear because once we have intersection product, this C1 will be in A1. I can actually intersect and get a class in A, E plus I, and then this will be a class in that chow indexed by a codimension, and the push forward is also defined. So everything will be actually Chern classes if X is non-singular. But you see, for the proof you'll see, so you'll ask, why is it necessary to, for example, do this definition as operators for for singular varieties possibly. Again, in the proof you'll see we are going to use this reduction very often, that replace, if I want to prove something for cycle, replace that cycle, assume that cycle is square bracket x. So here that this passing on to possibly singular varieties is going to be an important flexibility we need in the proofs. So even though your final interest may be Chern classes of smooth varieties, so this definition of Chern classes of operators is important to set up and prove this whole thing. So unfortunately, splitting principle I'll do next time. So that is that will not take long, and then this 3.2 also we will prove next time. Yes. Okay, so that is it.